Hello and welcome back to another video. In this video, we're going to be continuing on with something that we actually started in a previous video, video number 2 in this video series talking about the van der Waals equation and the generic cubic equation of state. So what we did in video 2 is we said, well, what if we have a situation and where we know the pressure and temperature for a gas, but we want to know its specific volume. Well, what we said was if we take a look here, and we have our generic cubic equation of state, which is P equals RT over V minus B, and then again minus A. The A parameter is dependent on temperature, and we have V plus epsilon times our excluded volume B here, and V plus sigma times our excluded volume B. And what we said here is that in order to rearrange this equation in order to solve for the specific volume V, that is done through rearranging the general cubic equation of state in terms of Z, the compressibility factor. Now the compressibility factor, just for a quick reminder, is equal to PV over RT. Okay? So what we did here was we rearranged this generic cubic equation of state into the in terms of the compressibility factor Z, and we ended up with a cubic polynomial in terms of the compressibility factor. So we have Z cubed, Z squared, Z in our constant terms here. And what we did was we went through and we multiplied out to determine all of our coefficients for each of the terms. So we have our Z cubed term and each following term here. So now what we need to do here is we need to actually solve this cubic polynomial to be able to solve for our volume here, our specific volume. And what we have here, and this was done in our last video, video 3 in this video series, was we were able to plot in Python isothermic curves. So pressure versus specific volume curves, and this is at isothermic temperature, so the same temperature on that curve. And what we're saying here is that because the liquid specific volume here and there is a vapor specific volume here, we'll actually talk about this in the next video. We'll use a Maxwell construction, which essentially what we do here is if we want to know the pressure on this curve here, what we'll do is we draw a line here across this curve, so a straight line, and in order to determine the exact temperature or the exact pressure there, this curve underneath, or this area underneath here and the area above, have to be equal. Again, I'll go more in depth to that in the next video, but essentially for this video, all we need to know that this is the exact temperature if this area and this area are equal. Now, what we do here is that we will be using Python in order to take the roots of this cubic equation. And we'll notice here that if we see here, we have a root here for our specific volume. So right there where our pressure line intersects our temperature curve, that is where we have a root there. We also have a root here, and we also have a root here. So if we're able to solve this cubic polynomial in terms of the Z, the compressibility factor, we'll know that we have 3 different roots that we get that will allow us to solve for the volume here if we simply just rearrange this expression here for the compressibility factor. So now we'll go ahead and go into Python in order to actually do the calculations and use a root solver to get our answer.
Okay, so now that we're in Colaboratory, we can go ahead and use something that is known as Cardano's formula in order to determine the roots of our cubic polynomial. Now, essentially what this is here, I have the document on the right here, and it explains to us how to use the Cardano's formula to get our roots from a cubic polynomial. So what it's saying here is that we have our cubic polynomial. So ours here is in terms of Z, the compressibility factor. However, here it's used in X, but it's the same principles apply. There's just different variables. So we'll have x cubed plus ax squared. So this a coefficient is the coefficient for our z squared. The The b coefficient is the coefficient for our z terms, and then we have our c constant terms here. And essentially what it is saying that in order to calculate our roots, first we will need to calculate these two values here. So a q value and an r value. And then what it's saying is we'll actually have two different situations here to determine the roots for our cubic polynomial. The first situation is saying that if r squared here, so this expression here, is less than q cubed, then we will have three different real roots by first computing this theta and then computing our three roots through these equations down here. Okay, so that's our first situation. Now I'll also have another situation in which we will have to calculate this a value down here as well as b, and we will have one real root, but we'll just go ahead and focus on this first one first that will give us three real roots. So what we'll need to do here is define a function that will return to us our roots. So we'll do something like cubic roots, since we're taking the roots of a cubic polynomial, and we'll have a, b, and c. So first what we'll do is we'll go ahead and just follow what the Cardano's formula tells us. So we'll calculate our q here. Okay, so we will have a squared, and this will be, we'll subtract 3 times b from this, so 3 times b, and this will all be divided by 9. And our r here, and I'm going to use a lowercase r just so that we're not confusing the ideal gas constant r here with this r value. It just helps me to not confuse them, so I'll use lowercase here. And we'll see that we have 2 times a cubed, so a to the third power. And then what we're going to do here is we're going to subtract from here 9. So we'll do 9 times a times b. And from here we will add 27 times c. Okay, so it looks like we're good there. These match up. Okay, we're good. And this will be divided by 54. Okay. So now what we'll do is we'll go ahead, and since we'll have two different conditions here, we have to write an if statement for our condition. So we'll say that if, again, our r squared here is less than our q cubed, then what's under that if statement is whether that's true, and then we'll also have another situation. So we'll say here that if r squared is less than q cubed, then we will first compute this theta value here. So we'll have theta equals np dot arc cosine. So I have arc cosine, and we will have r divided by, and the square root of q cubed is just q to the 3/2 power. So what we can say here, we can put in q to the 1.5, so just 3 divided by 2. Okay, so that allows us to compute our theta, and we'll go down here to calculate our three roots now. So we'll notice here that in order to calculate our three roots here, x1, x2, x3, we have this -2 square root of q cosine, and they are all subtracted by a/3. So what we can do here is we can actually enter in our roots, keeping all of the values that they have similar, and then make an array of what's in the parentheses here, so that it will just compute the three different roots all the same, and the only thing that's different is what's in the cosine parentheses. So we can go ahead and do that here. So we'll do roots, and that will equal, if we follow here, so we'll have -2, and this will be multiplied by the square root of q, so we'll go q to the 1, sorry, just 0.5, okay? And this will be multiplied by np cosine. And here, we'll go ahead and put in our array, so our array for the three different roots. Our first one will be theta divided by 3. Okay. Our second one here will be theta plus 2 times pi. So we'll have theta plus 2 times np dot pi. Okay. And this will be divided by 3. And let's see here. Okay, we're good there. And our last one here will be theta. And then we'll subtract from that 2 times np dot pi. Okay, good there. And we will divide by 3 here again. Okay. And lastly here, we'll have to add on the outside what all these terms are subtracted by. So we'll go ahead and subtract a divided by 3. So a divided by 3 there. Okay. So hopefully here we didn't make a mistake with our parentheses, but at the end, if we do get a syntax error from Python, we can go back and take a look at this, but I'm going to go ahead and move on from now. I'm not going to take too much time trying to analyze it. So what we'll want to do here is we'll have 3 different roots here, and if you watched at the beginning of the video, you'll notice that looking at our pressure versus specific volume diagram here with isothermic curves, if we draw our Maxwell construction line across here, which I'll talk about in the next video, but if we draw our line for the pressure, we'll have a root here, which will be the specific volume of the liquid, and then here we'll have just an artificial root, and this other root here that will intersect here at the end will be the specific volume of our vapor. So what we can do here is we want to go ahead and sort our roots so that they're in the correct order. And we actually have a function in Python that will allow us to sort these. So if we just do np.sort, again using the numpy, we can go np.sort and put in our roots so that it will sort them. Okay. So now what we'll have is we'll put in an else here so that we can go ahead and put in our second condition in the case that r squared is not less than q cubed. So for our second condition here, and again the condition would be if r squared is not less than q cubed, the Cardano's formula, again we're just following the formula and plugging in. So if we follow the formula, it tells us that if this is not true, then a here will equal negative sign of our r value. And this negative sign here, essentially what this is telling us that, let's say r is positive 1000. If r is positive 1000, then this value here would just be positive 1. If r is negative 1000, then this value here will just be negative 1. So it's just the sign of whatever value you have for r multiplied by 1. So we can go ahead and write a here. So I have a, and to use this sign function in Python, it is np.sign. Okay, and that'll be of r. And here this will be multiplied by the absolute value of r. So we can do np.abs, which will take the absolute value. So it'll be by r. And from here we will add. So we'll add r squared minus q cubed. So we'll have r squared minus q cubed. Okay, this will be to the 1/2 power, so we will raise this to 0.5, and then this entire expression will be raised to the 1 divided by 3, so we can raise this to the 1 divided by 3 power. Okay, so it looks like we match up there, so it looks like we're good. Okay, let me see here, if I add in our parentheses there, see if these match up. Yeah, they match up, so we should be good to go. Okay, then it says here that our b here also is dependent on the value of a. So we can do an if statement here actually within this line of code. So we can say that b equals 0. And I'll put a period here just so that since I'm writing strings and numbers here so that I don't get confused and really more importantly, so that Python doesn't get confused whether I'm writing a numerical value or a string. So if we say b equals 0, so b will equal 0 if a equals 0. And we have to put two equal signs here because this is a condition. We're not setting a equal to 0, it's just a conditional. So we'll say b equals 0 if a equals 0, else, so if a is not equal to 0, b will be, q divided by a. Okay? And what we'll want to return here, we see that if this is true here, this condition, our one real root will be right here. So we will return our a plus b and then subtract this a minus 3. So a minus 3. Okay? Go ahead and take this out here. Make sure that runs properly. Okay. So we'll add another line here. And now that we have set up our conditions to calculate our roots, we can go ahead and define a function that will return to us the specific volume that we're looking for. Now remember, in this problem that we're trying to solve, we are given the pressure and the temperature, but we want to solve for the specific volumes. So if we define a function that will return this specific volume, so cubic, we'll call that SV for specific volumes, and this will take in our A, B, and C parameters, or actually no, excuse me, this will take in our pressure and temperature, since that's what we have been given in this problem. Okay, so put a colon there. And what we'll need to do here, if you'll remember, if you watch the second video, and I briefly talked about it at the beginning of this video, but essentially what we did is we rearranged the general cubic equation of state in terms of compressibility, and we got a cubic polynomial in terms of the compressibility. So what we'll need to do here, since we're doing this in the same notebook, I'm going to go ahead and I'm going to add in our coefficients here for our cubic coefficient function here, because we will need that in order to calculate the compressibility factor Z, and then ultimately from there calculate the specific volumes. So we have that there, and we'll also need, okay, so we have that there, and what we'll need from here, since if you remember again, if you watch video 2, essentially what we'll be solving for is Z, and we have a cubic polynomial for Z. And what we'll want to return here, once we calculate the roots of the cubic polynomial Z, we'll want to not return Z, but we're looking for the specific volume. So since we know that Z equals PV over RT, we can say that V here equals Z times Z times RT, so 2Z times RT, okay, and divided by P. So that will return us our specific volume. So now what I need to do is go ahead and I need to first enter in the beta and Q parameters that we determined in the second video. Again, these are just parameters that helped us make the transformation of the general cubic equation of state in terms of the compressibility to be more simpler. So the beta value that we had was beta equals B times P, and this was divided by RT. Okay, and our Q value that we had, again, we just substituted this in to make our cubic polynomial easier. Our Q value was A divided by, it was divided by B times R times T. Okay? Now what we'll need to do here, if you remember, if you watched, again, the beginning of the video and in video 2, I wrote out all of the coefficients for our A, B, and C parameters for our cubic polynomial in terms of Z, the compressibility. So what I'm going to do here is I'm going to go ahead and write these out. And this will allow us to solve for the roots of Z and ultimately get our specific volumes. All right, so I just went ahead and went in and added in all of our coefficients here. Again, so we have our epsilon, our sigma, our beta, and q. And these coefficients here, so this first row here will be the coefficients for the A. So if we go up here, for the z squared term, the coefficients for B, for our z term, and then our constants. If you want to see how I actually went through and calculated these different coefficients, you can watch one of my previous videos in video 2 when we actually derived this cubic polynomial and got these coefficients. But simply I just went ahead and added them in here, so just for the sake of time. So I'll go ahead and run this just to make sure I didn't make any errors. So the parentheses look good, and I think the parentheses look good up here, but you never know with Python, so we'll go ahead and we'll try to calculate our specific volumes here. So if we go cubic specific volume, and we had to enter in a pressure and temperature again, because this is the problem that we're trying to solve if we're given pressure and temperature and we want to solve for the specific volume. So I'll go ahead and enter a pressure of 1 to the 7th and a temperature of 600 Kelvin. So if we press Shift Enter, okay, so there it works. So these are our 3 different roots, so our specific volumes. So we have calculated, and it looks like everything worked out okay here. So just in summary here, essentially what we did was we were given a problem where we knew the pressure and the temperature, but we wanted to know the specific volumes. So we needed to solve the general cubic equation of state in terms of compressibility Z. And once we got a cubic polynomial in terms of Z, we were able to take the roots of that cubic polynomial. So these are the coefficients here, and when we were returning these, we wanted to return it not as Z, the compressibility, but we wanted to return it as V. And in order to do that, we said that Z, since Z equals PV over RT, we just rearranged that, just some basic algebra. And if we return Z times R times T divided by P, that will be returning us our specific volume. So there you have it. Now we have successfully completed this problem. Thank you for watching.